Myself Shrey. Today I am going to talk about spotting motifs in an Alapana of Carnatic music. First I'll start about talking about the task what ma'am has already said. Then I am going to talk about saddle points, which are some features we have come up with. We use this to smooth the pitch contour. We use this to reduce our search space. Then I am going to talk about some of the conventional techniques which are used to solve this kind of problems. Then I will talk about some of the techniques which we are using in this work. Then I am going to talk about the approach which we are taking to solve this, to tackle this problem. Then I will show the results. So the task is we have given a motif in a big alap, and the task is to find this motif, all the instances of this motif in the alapana. So here is an example of a alapana of which is of 4 minutes, and the red shaded areas are actually the location of the motifs. So our job is to, given a query, our job is to find all the instances of this motif. So as you see, these motifs are distributed at a very irregular intervals. This is not a trivial task, as motif vary in terms of duration. As Professor Preeti said, it just not be because of the tempo. Some musician might decide to stay at a note for a longer time than others. So due to this also we have different durations in the motif, and these are the two motifs of Shankara Bharnam. They are the same motifs. So, and this is of Bhairavi. So as you can see, these motifs are laden with gam khas, inflected notes, and the rendering of this inflected notes might differ from musician to musician, and for the same musician also, when is in a same concert, from time to time also it can differ. So this makes this problem even harder. So before going into the techniques, I want to talk a little about saddle points. We have so these points are the points in the pitch contour where the first derivative is 0. So we have observed that these points preserve most of the raga information, as you can see from the images. The first figure is the pitch histogram of the raga Kamboji, and the second figure is the saddle point histogram. So we do lose a little information in the saddle point histogram, but still the raga information is preserved. So this is the motivation we had to carry on to use this saddle points, and we also use it to reduce our search space while looking for the motifs in the alapana. We also use this saddle points to smooth the pitch contour we have. So first I will play a line in raga Todi sung by Vignesh. Now we have used saddle points to smooth the pitch contour and reconstructed the melody. So it will not be the exact, but you will find some similarity. So these saddle points alone and the smooth pitch contour we are using in our task as a feature. So the conventional techniques which are used to tackle these kind of problems, similar problems, are dynamic time warping and its variant unconstrained endpoint dynamic time warping, longest common subsequence, and there are other variants too. I'll be talking about these techniques one by one. I'll be discussing the problems with this and why we cannot use these techniques as it is for our task. So the dynamic time warping does end-to-end matching. So it matches the query and the reference from start to end. As you can see the alignment, so the left endpoint of the query will match with the left endpoint of the reference, and same for the right point of the both. So this works fine if we know the start point and the end point of the phrase. But sadly we do not know. What we have is a 10-minute long Alapana and a 4-second motif. If we can, but we don't know. So what we do is we take a long window and we assume, okay, this motif will be present inside this window, and we just look for that motif in the shorter window, and we shift that window by some distance and then look for these motifs in these windows. So what we need is somehow a technique which can find the query and match it partially with the test. So there is a variant of DTW which is UDTW. So they are the same test and reference, but the entire query is partially matched with the most sensible region of the reference. So as you can make difference in the alignment also. Still we cannot use this technique because this works fine if we know the query exactly, but we do not even know, we are not even sure whatever we are querying for if that entire thing is a motif or not. We have encountered many places where we ask for some query, and there are many instances in the Alapana where the first part of the query or the last part of the query are present. So we also want to get those parts. So that would be possible if we can somehow match partially the query with the part of the test. So there is another technique, LCS, which has a power of doing this. As this is a simple example which shows how it matches PRSO, which is a part of the query and part of the reference. So it has that power, but the problem with this is it does not consider the local similarity into account. What I mean by that is P, R are very close to each other and they are matched, but the S is very far from R in the reference than in the query, same with the O. So what it does, it gives you just the longest common subsequence and doesn't consider local similarity into account. So there is a variant of LCS which is a rough LCS, rough longest common subsequence, which takes care of this. So it has all the power of LCS. It can match query partially with the partial reference, and it also considers local similarity into account. So as you can see from this figure, the query has been partially matched with the reference, and also it is taking considered local similarity into account. Next I am going to talk about a rough longest common subsequence. As I said, it's a variant of LCS, and how it differs from longest common subsequence is in longest common subsequence we look whether the symbols in the reference in the query, if they are same, we increment our cost function by 1, and this thing we do recursively. So in the end, the cost function, the value of the cost function is equal to the length of the longest common subsequence. So actually cost tells us how big the longest common subsequence is. In RLCS, the first thing we differ, we do not, so in LCS we want the symbols to be same. In RLCS we want them to be roughly same. So we have any distance measure, if they are very close to each other, or maybe their distance is less than some threshold, we say they are similar. and we do not increment the cost function by 1, but we increment by a value, we say delta, which will be greater if the symbols are very similar, and it will be less when they are a bit further apart. So result of this is that here the cost of RLCS does not tell you the length of the longest common subsequence, unlike LCS. So RLCS sort of gives you rough length of the longest common subsequence. So if you want the actual length of the rough longest common subsequence, you just have to replace this delta ij by 1. So if you do that, the end resulting cost would be the actual length of the rough longest common subsequence. So as I said, rough longest common subsequence considers local similarity into account, and VOR, width across reference and width across query are responsible for that. So these are smallest string containing the subsequence. So here it's like the subsequence is PRSO, and the smallest substring in query is PRESSO, which is of length 6. So that is our width across query. Similar the case with width across reference. And the intuition is larger the width across query, let's say lesser the width across query, denser is the distribution of my subsequence in the query. So with this, it's pretty clear that the distribution of the subsequence PRSO, the density of PRSO is less in the reference than in the query. So we use this VOR walk as a constraint and find a subsequence which is denser both in query and in reference. So this takes local similarity into account, and also as it is LCS, we end up matching partial query with partial reference. So here is the score computation. We have one more measure. Here we use the VOR and walk, width across reference, width across query. So the idea is if width across reference and width across query is high, we penalize the score. It ends up getting a lower value. And we also penalize if the rough length, remember Cij is the rough length, not the actual length of the RLCS. If the rough length of the RLCS is very less as compared to the query length, so n is here the query length, so then also score will end up getting the low value. So and there are other issues with the RLCS also. Here the row parameter, it tells us if the rough length is, let's say row is 0.8. So what we actually want the rough length to be greater than 80% of the length of the query. But we don't know what rough length means because it depends on the increment delta, and which depends on how similar the symbols which we are trying to match are. So it's not clear how to tune this row parameter. So we have modified RLCS so that such that it becomes easy. The tuning of row becomes easy. And as we can see here, Cij upon VOR, WRij. Cij is a rough length of the subsequence, but VOR is the actual length of the string containing the subsequence in the reference. So what will happen is the rough length would be less and the VOR will be high. So score, even if the sequences are similar, quite near, the score will end up getting a lower value because of this. So we have introduced a rough width cross reference where we increment when there is a rough match, we increment not by 1 but by delta. So this gives us the rough width across query and rough width across reference. So this doesn't change in the result much, but it just shifts the score value from lower range to a higher range. We have also made some other changes in the score computation. First, we have replaced VOR by rough VOR and rough walk by rough VOR, walk by rough VOR. And in the RLCS, we were just penalizing if the rough length of the RLCS was less as compared to the query length. But in the RLCS modified, we also look in, so CAIJ is the actual length of the RLCS. So we also look into that the rough length of the RLCS, how close it is to the actual length of RLCS. So if they are very close and still the rough length is less than the query, so still the score will not end up getting a bad value, not a lower value. So if actual length is similar to the rough length, very close to each other, and still the rough length is very less than the query length, it means though very less points have matched, but still they have matched with a higher confidence. And also this makes us the tuning of row parameter easy. So here we'll asking if the actual length of the RLCS is greater than some row times n. So we only look at the voice portion. We use a voice activity detector which is energy based, and we ignore the areas which are unvoiced like silence and other unvoiced areas. This also reduces the search space and makes our algorithm a bit faster. So we run RLCS in a two pass. In the first pass, we use only the saddle points of the query and Alapana and perform RLCS with it, and we get the potential motif regions, not the actual location of the motif, but we get a longer region where motif could or might not be present, and these regions are very less than the entire Alap length, and this phase of the algorithm is fast because we are only using saddle points. In the second pass, we use the entire smooth pitch contour and we try to locate the motifs in these potential motif regions which are written from the first pass. This part is slow. So in these two passes, what we are trying to do, in the first pass we are reducing, let's say our Alapana is of 10 minutes, we are reducing our search space to let's say 3 minutes or 4 minutes, and we are only looking in those areas. So these 3-4 minutes are very important. Here the chances that motif is present is higher than in other areas. So if we run a very fast algorithm and we reduce our search space, then we precisely match the pitch contour and localize this motif in the regions, in the potential motif regions. So these are some of our results. This is the query of Bhairavi, and we get that I am only showing the top 3 hits. The green color means these are labeled as correct as motif, so we consider them as true positives. Red ones are not labeled as motif, so we consider them as false positives. So I'll play the query again. So the topmost hit is, and the second most hit is. So the part, very small part is matching, but it's not a motif. And the third is, I'll play it again. For Shankara Bhandam, the query is, I'll play it again. So the topmost hit is a false positive and it sounds like. The second hit is true positive. The third hit is again a false positive. This is the query of Varali. So this is a true positive and the first hit. Next two are false positives. And the third one. So this is, I'll play the Bhairavi again. So just to this is an alap sung by Nedanuri. So we have found these motifs in this alap. I'll just play it one by one. So this is the true positive. This portion is a false positive. It is. This is another true positive which we have spotted. This is the another one. I think that's enough. Thank you.